I'm going to take you back to class, to school, to algebra. And that's probably the last thing that you wanted to do in a TED Talk today. Maybe you remember in algebra class that you learned how to solve small systems of equations in variables x, y, and z. And maybe they didn't tell you exactly what these x, y, and z were, and you were left with the impression that these equations were not particularly interesting nor particularly beautiful. But actually, equations like this are at the very core of science and engineering and all the algebra around them. And because each of these equations defines a relationship between these variables x, y, and z. And relationships and connections are all around us. Now, for that reason, we love them, and I want to share some of that love with you today. Now, maybe you remember how to solve these equations. You express most of these variables in terms of one other, here y, and after some manipulations, you get a final equation for y that you can then solve that gives you back x and then z. Now, that works really well for these small systems of equations, but perhaps you had these nightmares of going into class one day and your teacher writing down on the board this test equation and saying, go ahead and solve them. Now, the equations that I work with have thousands, if not millions, of variables, and obviously we would need a really big piece of paper and a lot of patience to solve it the way you were taught. So, of course, we don't. Instead, we use computer programs. Now, before we can use these computer programs, though, we need to reorder these equations a little bit. So we're going to write them really, really neatly under each other, and where variables are missing, for example, z in that first equation, we add it, but we multiply it with a 0. And then we explicitly write all the coefficients in front of it and write everything in terms of additions like this. And it seems a little bit silly, why would you do that? But now you see every equation looks the same. Something times x plus something times y plus something times z is something else. And so we don't have to write x, y, and z all the time. We just remember the order in which they occur. Right? And we store these x, y, and z in a little skinny table that we call a vector, like this. And then we store these coefficients, the 1s and the 0s, and here also the -1, in a separate table, like as I will show you in a minute here. Okay? So now the system of equations that I have is really just a table of coefficients, like this, and then this little vector with all these unknowns. Now, this table of coefficient we call the matrix. And the matrix is so famous, they even made a few movies after it. And like Morpheus says in this movie, the matrix is everywhere. It's all around us, even now, in this very room. So I want to give you a few examples of where matrices occur. And as first example, I'm going to take you to the San Francisco Bay. So here in the San Francisco Bay, some of my colleagues designed a really nice computer simulation of the tidal flows going in and out of the bay. And this is a really interesting simulation. It can show you, for example, salinity gradients in the bay, or maybe surface velocities that are good and useful for the America's Cup, which is actually what they did last year. Now, the flow is much too complex to understand and compute the velocity in every single point. So instead, we're going to be computing the velocities in a set of points distributed throughout the domain, and here the points are the vertices of these triangles. Now, through the laws of physics, we can relate the velocity in each of these vertices to velocities in neighboring points. There's a relationship between them. If there is a relationship, there must be an equation, and if I have a whole bunch of these equations, what do I get? The matrix. Now, if I write down this matrix, it would be extremely large and would have lots of numbers in it, so I don't do that. Instead, for every non-zero in this matrix, I put a little blue dot. Okay? And then what I get is a matrix like this that I can actually look at from afar, and I can see structure in this. Now we use computer programs to create matrices like this, or visuals of matrices like this, and these are called spy plots. And sometimes these computer programs, they have little Easter eggs in them. And so in one of these programs, when you type the command spy, you see this. Okay. Now we can do the same thing in your body. I didn't know if you realized this, but your body has matrices in them. And now we're going to take you to a simulation done by colleagues of mine in UC San Diego of blood flow through your aorta. Now the this blood flow model was created using CT scanning, the aorta itself. Okay, and besides the blood flow, it will also give you really interesting information about wall shear stresses that are important for blood clotting that you want to know about for bypass operations. And again, the velocities and the wall shear stress are computed in points distributed like this. And the matrix that comes out has a really interesting structure too. Now, search engines use matrices that tell them which words occur in which websites. And I'm going to take 4 randomly chosen words. Stanford, beating, cow. And the word egg. Right? And 5 websites that have 1 or more of these words in them. Okay? And so it's a website over cooking, over TEDxStanford, the Berkeley website. Now, what a search engine does, it creates a beautiful table where each row of the table corresponds to a word, and each column of the table corresponds to a web page. And if a word occurs in the web page, then you put a little 1. And if it doesn't, you put a 0. And what do you get out of this? A matrix. Now, in reality, these matrices are billions of web pages long and millions of words deep. And you need to be a pretty good mathematician in order to build a good search engine. So, but hey, you know now that it's a good field to be in. I want to earn a little bit of money. So here are those matrices. Now, a variation on this theme is shown in the next slide of a matrix. And here, every column and every row corresponds to a text document, and there is a little blue dot if these 2 documents have a lot of words in common. So this is a connection matrix for 20,000 documents from the classics. We could do the same with web pages. We could put web pages both along the rows and the columns and put a little blue dot if there is a hyperlink from one web page to another. And what you're looking at here now is the Stanford and Berkeley web domains, with Stanford nicely clustered, Berkeley nicely clustered, but there is communication between these 2 because there are some blue dots in the other sites as well, which is actually kind of surprising since we keep beating them. But they still want to communicate with us. Now, matrices are also in your brain. Here you're looking at white matter fibers that connect gray matter regions in your brain. And looking at this, I could create a matrix that has gray matter regions in your brain along the rows and the columns and show connectivity between these regions. So here you can stare at this matrix for a long time and understand how your brain is all connected up. So matrices are everywhere. They model systems of equations, they're in your brain, they're in the search engine, and as mathematicians we work with them daily, and we really love them. And these matrices, they have personalities for us. So when I prepared for this talk, I asked all my students, what are your favorite matrices? And here are a couple that I wanted to share with you. So we have some matrices that are sparse with lots of zeros, and then the top right are matrices that are symmetric. And symmetry, as we know, is always signifying beauty, so we love those. And then there are matrices that are symmetric and sparse and are sort of banded like this, so they're really fantastic. And then there are other matrices which I really like, and sort of blockish structures. But the very winner of this competition was a matrix we called the Toeplitz matrix. And that comes up a lot in signal processing. And it may look like much to you, but every diagonal in this matrix has a constant number, and it makes it much easier to work with. Now, what about the nastiest matrices? And here is the one that we hate the most. In the 2 elements that are very different in size, it makes it really hard to work with. We call them ill-conditioned. But the worst matrices in the whole world are very, very, very large matrices that are ill-conditioned. And enabled to work with those, we need to write specialized computer programs. And so there are millions of lines of codes everywhere, that people wrote in order to manipulate these very large matrices. For example, the matrix you heard about this morning for climate models, which is a very nasty matrix indeed. And these lines of code, they are behind a lot of the simulation tools that you will see out there and that people use in science and engineering. Now, I said I was going to talk about the beauty of math, and maybe so far you're not super excited. You're saying, well, no, I see some blue dots on the screen. That's not very beautiful. So let me show you how we put beauty into mathematics and algebra. Here's a matrix, and I'm going to associate a number with each row and column, 1 through 4. right? And every number is now going to be related to a node or a little ball. There's going to be 4 of them, 1, 2, 3, 4. And now whenever I have a non-zero in the matrix, for example, at positions, in the first row, positions 1 and 3, it means there is a connection between 1 and 1 and 1 and 3. Now 1 and 1 doesn't show up, but 1 and 3 does. So the next row gives me a connection between 2 and 4. The next row gives me an additional connection between 3 and 4. And now I draw a connection, the last one, between 1 and 4. Now we have a little graph that comes out, and that looks much more pleasing than just a table with numbers. But you can just imagine if I have a really big matrix with lots of non-zeros, what a mess that would be. All these little balls and all these little links between them. So here's the trick. Whenever there is a link between these 2 balls, we imagine there is a spring that pulls these balls together. But at the same time, we give the balls also repelling charges, so that when they're not connected by a link, right, that they repel each other, push each other away. And then we just let things go and sort themselves out. And what looked to be a mess, just a simple matrix that was messy, is turning into a beautiful structure. It just finds its minimum energy, and out comes this fantastic geometrical figure. And when we study them, we can actually see some of the properties of the physics even coming out in these pictures. Now we can apply those to lots of different matrices, and I want to share some of the prettiest ones. Here's people and the web pages they like. Modeling of a lung, the matrix corresponding to that. Financial portfolio analysis. Shallow water models, estuary flows, and so on. The Stanford Web. MRI modeling. Analog circuits, makes your hair stand up. Tidal flow models. And my very favorite one, this is called the Galaxy, that tells you how the catalogs and the subcatalogs in the Library of Congress are all connected together. So that math that you learned at high school, with these equations that you didn't like so much, that's behind everything. It's beautiful, it's omnipresent, it's everywhere. And who knew you could make such pretty pictures? Thanks very much.